Okay, so oh no. Can't we erase all that? Do I? Oh. Okay, so I'm gonna start with the NMR for this for worksheet number 6 because we didn't get to finish that one. I didn't give you the formula and I didn't give you the splitting patterns or the integration just because I forgot to. So I'll give that to you right now. But I wanted to say like the first strategy for doing a roadmap is just looking at your NMR compound that you like that she has written out for you. So I'm gonna call this compound A. I'm gonna call this compound B, and I'm gonna call this compound C. Okay. So compound A is what we're solving for with the NMR on the next page. And what I like to look for in my roadmap is anything that's pointing towards compound A or anything that's pointing towards my NMR compound, which I see that compound B has an arrow pointing towards it, telling us that it's going to have a bromine on compound A. Why is that? Because we have HBr and radical HBr. This peroxide tells us it's a radical. So I'm going to put radical reaction. And that compound A may have a bromine in it. Okay. I'm going to come back up here and I'm going to write that it has a bromine. And I'm still not going to give you the formula. That was like for a purpose because this one was one of the easier ones. But I am going to give you the splitting pattern and the integration. Okay, cool. Okay, so then, what was I going to say? I'm going to put splitting pattern up here and integration. Integration tells us the amount of hydrogens that are on the carbon that we're talking about. That's the number of hydrogens. Splitting pattern tells us, let me write the formula for you. Splitting pattern is n+1 equals blank. And this is where we insert the name like triplet, sextet, or triplet again. And so what solving for n is going to tell us is the amount of hydrogen neighbors or the amount of hydrogens on our carbon neighbors. Okay, cool. So then the first thing that I like to start with on the NMR is I look for something that could be my terminal carbon, which is something that would have 3 hydrogens around it. And I see that, I'm going to label this carbon A, B, and C. I see that carbon A has 3 hydrogens as an integration. So I'm going to write carbon A with 3 hydrogens around it. I do my splitting pattern formula, which is n+1 is equal to, and it says it's a triplet, so triplet, or 3. Solve for n is equal to 2, so that we know that we're going to have 2 hydrogens on our carbon neighbors. So right next to carbon A, I'm going to write a carbon with a integration of 2 hydrogens. There you go. We want to look for the next carbon that we're talking about, this carbon right here. And so the first thing that we would look at is the integration. So something with 2 hydrogens, and both B and C are giving us 2 hydrogens. So then the next thing that we look at is the splitting pattern. So let me highlight this. This carbon can't be a triplet because a triplet tells us that we have how many neighbors? Tells us that we have 2 neighbors. And to the right of the carbon that we're talking about, we already have 3 hydrogen neighbors. So it can't be letter C, but it can be B. So I'm gonna label it B. B is a sextet, meaning it has 5 neighbors. Oops. Five neighbors. So then I'm going to draw another carbon right next to it with 2 more neighbors to complete those 5. So 1, 2, 3, 4, 5. This is the sextet, and we just confirmed that. Okay. The last carbon or the last splitting pattern that we have here is a triplet, so with 2 hydrogen neighbors, and this, I'm going to label this one as carbon C. We know that we can confirm that this is carbon C because it says that it's a triplet, 2 hydrogen neighbors, count the carbon, the hydrogen neighbors, count the hydrogen neighbors, there you go. So 1, 2, we're good with that. And we cut it off here. Okay. We cut it off because we know we can't have more hydrogen neighbors. And so we have one more piece of the puzzle, and that was the bromine. So instead of cutting it off there, I'm going to erase all this. Carbon. I'm going to touch the bromine to the end. And then that's another thing that we can confirm with. So we can confirm this carbon that I'm underlining right here is carbon C because it is the most downfield atom on our NMR. So downfield. And what does that mean? It means that it's next to something electron negative or something that's just pulling in electron density towards itself. So electronegative next to electronegative atom. Okay, cool. So this would be my NMR compound. I'm gonna make it prettier. There we go. That's what that looks like. So we find our NMR compound and we can input it into square A. Okay, cool. So then whatever compound B is, we had a radical bromination reaction. And what we know about this reaction, HBr and the peroxide, is that it follows the anti-Markovnikov rule. Anti-Mark. So let me just give you an example of what Mark does again. So this is what Mark looks like. Markovnikov says, put the hydrogen in least substituted carbon on the double bond to make the more stable carbocation. And so in a normal HBr reaction without the radical, this is what that follows the Markovnikov rule. This is what it'll look like. This double bond is going to take this hydrogen, break off the bromine, putting the hydrogen in the least substituted position to make a more stable carbocation. And then let me just finish it off. Bromine comes back and attacks on this product. Okay, cool. So this again follows Markovnikov. We can see that this does not look like this at all because on our compound that we wrote, if we had the double bond right here, it would have put the hydrogen on the most substituted compound. So what I'm going to do is I'm going to write the product for B. Pretty much the same thing. But this time, because of anti-Mark rule that it has, I'm actually not going to show you the mechanism for this one. Because it follows the propagation, initiation, termination. So that would be like a lot, but just go over that in review. Just know that the radical mechanism adds the hydrogen to the least substituted. I'm putting the radical on the most substituted. I flipped that. Okay, so puts the hydrogen in the most substituted and makes the most unstable radical. Then bromine comes and has a radical reaction to form this right here. So point of all of this was to show you what anti-Mark was and to show you how to get B. Okay. Let's go back to C. Potassium tetroxide. It's a big bulky base. We have a good leaving group. So our big bulky base is going to come in and deprotonate this hydrogen. Hydrogen is going to put its electrons to a double bond, and we're going to break the bromine off. So we form a double bond again. There we go. A, B, C, and let's move to D. Okay, so in D, you have a diene and you have a dienophile, and you have heat. So we know that we're going to undergo Diels-Alder reaction. So for this one, I think it always helps to do the mechanism for this one, and it's kind of easy to do the mechanism for this one just because all the steps are concerted. So I'm going to redraw it to make it easier for me to see. I'm going to number my carbons because numbering your carbons, or the ones that will, the only carbons that will undergo the Diels-Alder reaction are going to help you in how to place the substituents on your new compound. So I'm going to do carbon 1 checking, carbon 6. Oh, I'm sorry. I have to draw it from the double bond. The double bond is breaking and forming a bond to carbon 6. Here, the double bond is breaking and forming a bond to carbon 4. The double bond between 3 and 4 is going to resonate between 2 and 3. And then we draw a product. So like always, we're forming the cyclohexene. I'm going to number my carbons. So 1, 2, 3, 4, 5, 6. Okay. We already know that we resonated the double bond from 3 to 4 to 2 to 3. So I'm going to put my double bond between 2 and 3. Okay. Then what we need to do next is see how the substituents on the diene are, like what the configuration is. So the substituent on carbon number 1, or the substituents on the double bond between 1 and 2, are both facing the same way. So let me draw up here. We know that when they're facing the same way, they're cis. Cis. There we go. Also known as Z. And then one of the things that they always say is like same side, because they're both of the substituents are facing the same way. And then you have trans, also known as Z. They have nothing to remember this by, so just memorize this one. No, if it's not cis, if it's not Z, then it's E. So then I'm going to say that both of these are here. This substituent are pointing both down. So cis, we're going to name it Z. These substituents are pointing both up on the double bond, so we're going to say Z as well. So since they're both Z, you're either going to put them both on the dash or both on the wedge, your decision. I'm just going to put it on the wedge. So carbon 1 substituent is an alcohol. And put it on a wedge. Carbon 4, the substituent is NO2. Put it on a wedge. Okay. If they were different, like if it was Z and E, then one of them would be on the dash and the other would be on the wedge. If they're both E and E, they're both either on the dash or they're both on the wedge. Okay. Okay. So then we have one more substituent, the substituent popping off of carbon 5, which is just a methyl group, and there's nothing to compare to. There's no other substituent on our dienophile. So you can just put that in whatever stereochemistry you want. So there's like a lot of stereogenic centers on this compound. There's a total of 3, I believe. And so there's going to be a lot of ways that you can orient your substituents in space. So as long as you have these two substituents, these right here, on the same either dash or the same wedge conformation, or yeah, same in space, then you're good. You should get this right. So I can, on carbon number 5, I'm just going to do a wedge. Doesn't matter. It's just a method. Okay, cool. I could have done it on a dash as well, but this is what I chose to do. Next one, we're going to go down to, let's go down to E. This will be F, and this will be G. Okay. This one was one that a lot of the students in my past semesters would get wrong. But all you have to really see here is that this is your strong base, and you have a really good acidic proton on your cyclohexene. So then you're just going to do acid-base reaction and deprotonate that. So I'm going to show you the intermediates. Negatively charged oxygen. This is what happened with the first reaction. And the second reaction is just a alkyl halide, so it has a good leaving group. So then if I write my alkyl halide, we see a good electrophile and a good nucleophile. So my nucleophile is going to come in, attack my electrophile, and pop off the leaving group. This will be my new product. Keep everything the same. This has a total of 1, 2, 3 carbons, so make sure that you don't drop any. 1, 2, 1, 2, 3. There you go. Okay. Again, on this one, we have a S-cis diene, and we have a dienophile. So we know we're going to undergo Diels-Alder. Just looking at this one is a little bit intimidating, but just because it's we already have a cyclic compound. Just do your mechanism and number your carbons, and it shouldn't be too bad. So 1, 2, 3, 4, 5, 6. This double bond is going to break and form a bond to carbon number 6. This double bond is going to break, form a bond to number 4. This double bond is going to resonate between 2 and 3. Remember that this one is breaking to form a bond. So we're no longer going to have that double bond there. I'm going to try everything else the same. We know that it's going to form another cyclohexene fused to this ring. And then don't forget to put your double bond between carbons 2 and 3. Let me number just in case. 1, 2, 3, 4, 5, 6. And we're good. We're good with that one. Okay, then back to compound G. Here we're reacting a compound with PBr3. So if you go back to OChem 1, it's your chapter 9 alcohol chapters. We know that PBr3, all it does is that it's going to substitute the OH group for a bromine. So this one won't be too hard. Try everything the same. And just switch the OH group for bromine. So, okay, cool. Again, if you have any questions on the NMR, I have office hours. You can go visit me in those, or you can ask me after our sessions. Cool.